In this video, I'm going to solve a polynomial inequality, and this is a more challenging polynomial inequality than the previous ones for a couple reasons. First of all, notice one side is not 0, right? All the other polynomial inequalities had one side equal to 0, and the second thing is all the other polynomial inequalities were factored. So what we're going to have to do is basically make those two things happen. So step one is one side must be 0. So this is just like solving a polynomial equation. You have to get one side equal to 0 and then factor. So same thing here. So let's make the right side equal to 0. So 2x cubed, and then we'll subtract x cubed from both sides. So if I subtract x cubed from this side, it will get rid of that term. Minus 3x squared, and then we'll we'll have to add x squared to both sides. Minus 4x, and then we'll have to subtract x from both sides. And then we have plus 3, and then we'll have to add 3 to both sides. Okay. On the right side, we'll then have 0 because we subtracted this, added this, subtracted this, added this. Okay, so adding my x cubed terms, I have x cubed. Collecting my x squared terms, I have minus 2x squared. Subtracting these x terms, I have minus 5x, and adding these constant terms, I have plus 6, greater than or equal to 0. Good. Cubic polynomial. Step 2, I must now factor. Okay. So I'm going to have to factor. If you let. So this is the polynomial I'm now, or the inequality I'm solving. So let p at x equal this polynomial on the left side. I should have an x there. Okay, and we want to solve for when this is 0, so in order to do that we have to factor. So we have to use Factor Theorem, meaning we've got to guess a factor. So guess, if we let that equal to 0, guess x is equal to, and remember when you're guessing, you're guessing factors of the last term, so numbers that divide 6. So numbers that divide 6 are 1, 2, 3, 6, or the negatives. Negative 1, negative 2, negative 3, negative 6. I'll start with the 1 and evaluate the function at 1. So p at 1, maybe I'll get lucky. So I have 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6. So 1 cubed is 1, minus 2 times 1 squared is 2, minus 5 plus 6 equals 0. Great, we're lucky. Since p at 1 is equal to 0 by the factor theorem, that means that x minus this number here, minus 1, is a factor of p at x. Okay, so we know one factor, right? We're trying to get all the factors. We're trying to write it in factored form. We know x minus 1 is one of those factors. So to get the rest, we need to do long division. X minus 1 divides x cubed minus 2x squared minus 5x plus 6. So what times x gives us x cubed? X squared. So x cubed minus no, there's no 2. Minus x squared. Subtract. So these two go away. Minus 2x squared minus minus x squared is minus x squared. Bring down the minus 5x. What times x gives us minus x squared? That'll be minus x. So multiply minus x by this binomial. So minus x squared plus x. Subtract. These go away. We have minus 6x. Bring down the 6 plus 6. What times x gives us minus 6x? It'll be minus 6. So minus 6x plus 6 equals 0. That's good. It better be 0 if this is a factor, which we said it was. So we know that x cubed minus 2x squared minus 5x plus 6 is equal to x minus 1 times the quotient, x squared minus x minus 6. So now we want to factor this thing as much as possible. So we know one factor is x minus 1, and now we can just factor this using quadratic factoring, simple trinomial factoring. So what multiplies to negative 6? So our product must be negative 6, and our sum must be negative 1. So what numbers multiply to negative 6 and add to negative 1? So those numbers would be negative 3 and positive 2. Okay, so we were trying to figure out when is this equal to 0. So it's equal to 0 when x minus 1 equals 0, when x minus 3 equals 0, or when x plus 2 equals 0. So when any of those linear factors are equal to 0. So x equals 1, x equals 3, and x equals minus 2. So going back to the original equation, the original polynomial inequality. So this is the inequality we're trying to solve. So now we've said that that's the same. This inequality here, the left side, is the same as this thing over here. Maybe I'll write it in blue. So we know this is the same as x minus 1 times x minus 3 times x plus 2 bigger than or equal to 0. Okay. So now we know that the x-intercepts, let me just go down. Can I fit it all in? I just figured it out down here. Remember, x was equal to 1, negative 3, and negative 2. So that was the x-intercepts from here. Okay. So now if we want to do this by graphing, we're just sketching a cubic with a leading coefficient, which is, there's no negative in front of this, so the leading coefficient is positive. So the x-intercepts are 1, negative 3, and negative 2. Okay, so we know we're going to go through here, here, here. Leading coefficient's positive, meaning we go up as we get bigger, as x gets bigger, and down as x gets smaller. I'm going to cross the x-axis here because the order is 1 on each of them. We want to know when it's positive or 0. So it's positive when it's above the x-axis, which would be here and here. So therefore, x is in the intervals from negative 3 to negative 2. We're going to include negative 3 and negative 2 because they make it equal to, or from 1 to infinity. We're going to include 1 for the same reason we said before. Okay, so that's how you solve this inequality. Just so you see it, if you don't want to even do it this way, that's fine, but if you wanted to do this using a chart, you'd go from negative infinity to negative 2, negative 2 to 1, Alright, I know I messed up. So my chart, I wrote the wrong one here, right? This should have been positive. I'm not redoing it, so I'm just going to erase this here. So I graphed the wrong x-intercept. So maybe you noticed that I had done that. I don't know. So my x-intercept should have been, the solution down here is not right, obviously. So my solution should have been, my x-intercepts were actually 1, 3, and negative 2, not negative 3. So 1, 3, and negative 2. But we still have that same shape, down as you go to negative infinity, and up as you go to positive infinity. So it's actually this interval and this interval which are positive. Therefore, x is from negative 2, which is what I had before, but now all the way to 1, and from 3 to infinity. Okay, so that's the correct solution set. So that's what happens. Make sure you get the x-intercepts right, otherwise you're going to get the wrong solution set. So going back to my chart, which I was going to do. So now I have to go from negative 2 to 3. Oh, sorry, not to 3. To 1, I would have to go to. And round bracket. From 1 to 3, and from 3 to infinity. List all my factors. X minus 1, x minus 3, x plus 2. In this interval, I'm not going to run through every value. If you want to pick values and work it out, you can do it. I'm just going to write down what the signs are. Negative, negative, this one would be positive. This one would become positive. This one's still negative, positive, and now they're all positive. Okay. Now if you look at the product, so the product, remember that the function p at x was the product of these three things. 3 negatives make a negative, 2 negatives and a positive make a positive, 2 positives and a negative make a negative, and 3 positives make a positive. We want to know when is this bigger than or equal to 0. So it's bigger than, well, it's bigger than 0 there, and it's equal to 0 at all these sort of points here, at negative 2, at 1, and at 3. So therefore, x is in the intervals from negative 2 to 1, including both negative 2 and 1, and from 3 to infinity, including 3. So looking at this interval, looking at this interval, same answers, just different method. Okay, so whichever method you like is fine. One thing I'll say about the chart is, remember in the graph where I had actually messed up my interval, where I'd, instead of 3, I'd put negative 3. You might notice when you do that, that these negative numbers and positive numbers in that interval don't actually work out, because you won't have a nice pattern. Like if you notice, like if you do enough questions like this, you'll notice there's a pattern where 1 changes every time. But if you sort of mess up on your interval like I had done, the good thing about the chart is you might notice the pattern might get messed up. Or really what's happening is one interval, it would be both positive and negative in that interval, depending on which number you picked. So you might notice that that happens. So that's one advantage to doing a chart. If you mess up your intervals, if you factor wrong or write the wrong x-intercept, write it negative instead of positive, like I did, then you might notice. So that's one nice thing about the chart.